In today's video, we will be going over Chapter 3 and 4 from Math 277. This week's content covers different components of motion relating to space curves, as well as talking about some example problems that include real-life examples. So we'll get started with this section. Before we continue to this section, it's important to know that you will need to know how to do cross product and dot product because we are using those as vector operations in this section. So make sure you know how to do that. If you don't, I'm sure some of my videos in statics and in physics have covered vector operations. So you can check out some of those videos and see if you find what you're looking for. So I'm going to go into this assuming that you already know how to do cross product and dot product and then you're comfortable with it. Okay, so the very first thing that I want to talk about is tangent unit vector. So unit vector has a magnitude of 1 and it defines direction for a vector. So if you had a unit vector for vector A, for example, they'd both be pointing in the same direction, where A is just a scalar multiple of the unit vector. So the unit vector is just used to establish direction. So with that knowledge, a tangent unit vector, as the name implies, is tangent to a space curve C. So if I gave you this space curve right here in this direction, your tangent unit vector is going to be tangent to a point on the space curve. So there's two ways we can define this value. First way is to say that it is our velocity over our speed of a particle, which is also equal to saying the derivative of position over the magnitude of the derivative of position, which we know just to be velocity. So that's why I wrote it like this to start. Next up is the principal unit normal. So if I were to draw this system again, and we have our space curve C. So we already drew our tangent. We know our tangent is tangent to the curve. Let me draw that better. So now we're going to introduce our principal unit normal. We're at the point of tangency, so where the tangent line brushes the space curve. Principal unit normal will point perpendicular to the tangent vector. So points perpendicular to the tangent line or tangent vector at point of tangency. And we will represent this with the equation equals B cross our tangent. So we don't know what B is yet. We will come back to that. This is our simplified equation that will make it easier to solve, but if you want it in a more general format, it's equal to the derivative of our tangent over the magnitude of the derivative of our tangent vector. So two ways to express principal unit normal. Next, we're talking about curvature, which we define with a K. So if we had our space curve C, curvature basically is just going to follow, let's use a different color. is just going to be following that curve. So this is represented by Greek letter kappa, kind of just looks like a K. And this is defined by the equation velocity, cross product of acceleration, the magnitude of those, over speed cubed. So this is our curvature K, and this follows curve C, same direction. And it defines how rapidly a curve turns, or how rapid a tangent turns, sorry. So that's basically saying how fast a tangent line is moving. So if we drew a tangent line here, the next point tangent line here, next point tangent line here. So this basically just defines the rate of how that tangent line will turn across that curve. Radius of curvature is defined by 1 over kappa, and we use symbol rho for it. So if I were to draw that space curve again, radius of curvature, rho, basically defines a radius of a circle that is tangent to the concave part of our curve. So this would be rho here. Sorry, that says curve. I'll write that better. Okay, I've got a few more left. So the unit binormal vector. So this one is similar to some of the other ones we've talked about. So if we have our plane here, for space curve here. So we had our tangent vector here. Perpendicular to that, we had our normal. And now we're adding a new element, our binormal vector, which makes a 90-degree angle with both of them. So this is orthogonal to both our tangent and our normal vector. So it's orthogonal to the tangent and normal unit vectors. Oh, sorry, I missed a little note up here. Sorry, I just wanted to elaborate for our previous question for radius of curvature. If we flipped the equation we were given for k, that would be speed cubed over magnitude of v cross a. Sorry, forgot to throw that in there. Okay, sorry, going back to binormal vector, the equation that we use to define it is b equals t cross n, which is also equal to v cross a over the magnitude of v cross a. Okay, so if you take a look at this part of the equation, if you know a thing or two about cross product and vector operations, you know that when you take the cross product of two vectors, it produces another one that's perpendicular to both. right? So if we went back to our physics video, if you checked out I believe, week 2 of physics videos, I talked about cross product with right hand rule. So if I were to orient my hand, the fingers of my right hand along the red tangent vector, and I curved it towards the n, our second vector, it produces a vector b that comes out of the page, right? Or in the positive z direction. So if I were to illustrate that, so if I started by pointing my fingers along T, this is just some bonus knowledge. You don't need to know this, but I think it's nice to kind of always draw it back. And if you were to curve your fingers towards N, you see that your thumb points out. So thumb points out, and that represents our B, if you guys can see that. Okay, and last couple parts of our curve, we have torsion. It's a bit hard to see. Let's not use that color. So torsion is given by Greek letter tau, and we represent this by velocity cross acceleration with the dot product of the derivative of our acceleration over the magnitude of our cross product of velocity and acceleration. So torsion is basically how much it bends away from something. Okay, let's talk about normal component of acceleration. So if we took a look at that same space curve again, and let's say we had an acceleration vector in this direction. The normal component of acceleration would be, would look a little something like this. So I'm going to talk about both of these components together because it just makes a little more sense. So that's our normal component. If our tangential component looks like this, tangent to the curve that our acceleration originates from, and we know that there's a 90-degree angle between both of those. So the formula we use for our normal component is V cross A magnitude over speed. In that same vein, the one that we use for the tangential component of acceleration is V dot product of A over speed. So there you have it. That's 8 different equations that we can use to describe motion on a space curve. So quite a bit of steps are involved when we actually solve these. So we're going to go through a couple examples and work from the start. Okay, so this question wants tangential and normal components of this space curve here, of this function. So let's write out what we're given. And this is going to call you back to a lot of chapter or week 1 material where we had to create functions for position and create velocity and acceleration equations based off of it. So we know that to find our tangential component, we need velocity over speed. right? So let's use this equation and find velocity. So velocity, we know, is equal to the derivative of our position. So that's going to give us 2t in the I direction plus 1j plus t in our k direction. Let's find our speed. Which is each component squared under the square root. That's equal to 4t squared plus 1 plus t squared, which is equal to wait, no, sorry. I'm just going to keep it under the radical. Okay, so we are given what our value of t, of time, is, so then we can solve for our velocity. And when we plug that in, so that is 8 in our I, that's just going to be 1, and then this is 4 for our speed. So we said that was 5, then, oh, this is 4. It's 4 squared plus 1 is equal to 5 times 16 plus 1, square root of 17. And we can double check with actually, hold on, no. So, can get a little tricky with some of these ones. Rather than using our variable to define speed, it's better just to find what velocity is first and then take our magnitude. So we said velocity is, once we plugged in, it's equal to 8, 1, 4. Then I would just take my speed from that. Sorry for the confusion. So then we'll do 8 squared plus 1 squared plus 4 squared, and that is equal to square root of 64 plus 16, and that's square root of 80. Sorry, square root of 81. My bad. So that is just equal to 9 for our speed. So now we can solve for our tangential component, or tangent unit vector, sorry. So that is 8, 1, 4 over 9. And this is equal to 8 over 9, 1 over 9, 4 over 9. Okay, so that's all there is to it for our tangent unit vector. And now let's find oh, no, wait, hold on. Sorry, I believe I misread the question. So this is just some nice practice. I actually misread the question. We're not finding our unit vectors, we're finding the components of acceleration. So never mind that. It's still good practice. I'm going to keep this here. Why did I erase that? I actually could have still used that. So I'm going to keep this here because we can still use it. All right, we just don't need this right now. Okay, So now we can find acceleration from our position equation. So let's do just that. So we're going to take this and we're going to take it down to one more derivative. So that's 2I plus 0j plus 1k. And then when we plug in for our values, that will give 2, 0, 1. So we know that for our tangent component of acceleration, we are going to need our velocity, take a dot product with a, and our speed. So we can solve that on our own right here. So we have 8, 1, and 4. Take it with a dot product of 2, 0, 1. And then that's over our speed, which we found to be 9. So that is equal to, so 8 times 2, 16, plus 0, plus 4 over 9. And this is going to be equal to 20 over 9. And now for the normal component, we need the cross product of velocity and acceleration. So we'll find that on our own separately, and this is over speed. So let's just break off for a second. We'll break off for a second on the side, and we'll find the cross product of v times a, and then we'll take its magnitude. So the first one is velocity, so we'll put those in for the second row. And then we have acceleration, so this is going to give, so that's going to give 1I minus, in our j component we have 8 minus 8, so then that's just 0. And in our k, 0 minus 2. So that's what our cross product is, and when we take the magnitude of that cross product, that's going to be 1 plus 0 squared plus negative 2 squared, so that is equal to square root 5. So let's work that back into our normal component of acceleration, and that's root 5 over 9. All right, so sorry for the confusion at the start, but we will be using this in our next couple of questions. We're going to be using the first set of 6 different equations that describe curves. But that's how you can use velocity and acceleration to find the tangential and normal components of acceleration at a given time interval. Okay, so next question. We have a space curve C, which is given by this equation here. So that's cosh t in our I direction minus sinh t in our j direction plus t in our k direction. First things first, I'm going to find velocity. So velocity so derivative of cosh is sinh, and this is negative cosh plus 1k. We take acceleration, that's cosh t minus sinh t in our j direction plus 0k. So we want to find our tangent, normal, binormal unit vectors, as well as curvature, radius of curvature, and torsion at t equals 0. Okay, so let's start things off. Let's find our tangent unit vector. So then we found that to be, so I'm going to do one more thing. Let's do speed, which is equal to squared plus this identity here is equal to 1. So that just equals square root of 2. So when we plug in our velocity, so then that's sinh t minus cosh t 1 over our speed, which we just found to be square root 2. When we plug in for t equals 0, we get 0, and this turns into negative 1 and 1 over square root 2. So then that's just 0, negative 1 over square root 2, 1 over square root 2. Next up is our normal. And we define that by saying b cross t. So I think it's easier to find b first. So let's do that. So another equation we're given for b is v cross a over the magnitude of v cross a. So let's just find that on our own on the side. So everything that's on this side are just separate equations that we do in order to find our other stuff. Let's do v cross a. And I'm going to plug in for our values. So I, j, k. So for velocity, when we plugged in our values, that's what we got up here. So that's 0, negative 1, 1. For acceleration, cosh 0 is 1, negative sinh 0 is 0, and then we have 0 at the end. So we have 2 zeros over here, so that means we can just take this cross product here to be in our j direction. So then that equals oh, no, sorry. Okay, so if we took I, we have 2 zeros over there. So I think the only ones that will work we'll do j. So we have 0I, and then this is minus 1 minus 0. So it's 1j minus 1j. And then when we do for k, this is 0 minus negative 1. So that's positive 1k. So when we take the magnitude of that cross product, that's equal to 1 squared plus negative 1 squared, which is square root 2. So let's put that back into our binormal. So then this is, so we had 0, negative 1, 1 over square root 2. So then that's 0, negative 1 square root 2, and then 1 over square root 2. Sorry, I messed up on one of the signs. This meant to be plus. Okay, so now let's find our normal unit vector, which was given by b cross t. So I'm just going to do that on the side. So b cross t. So b, what did we get? We got 0. Then we had 0, negative 1 over square root 2, 1 over square root 2. Okay, so then this is, so it's only going to have an I component because we have a row of zeros. So that's 1 over 2 minus 1 over, plus 1 over 2, which is equal to 1, if I'm not mistaken. And we said this was only part of our I, so that leaves 0 in the other ones. So that is 1, 0, 0. Okay, so that's it for our unit vectors. Let's move on to radius of curvature, which is equal to magnitude of v cross A over v cubed. So then that's equal to, so we found out what our magnitude is, that's square root 2 over our speed, which was square root 2. So that is 2 square root 2, which equals 1 over 2, because these can cancel. All right, now for radius of curvature, rho is equal to 1 over k. So then that's just like flipping it over, so that gives us 2 for the reciprocal. And finally, torsion, which is equal to, so we're going to have to do one more operation. So this is v cross A, dot product of dA over dt. So we need to find that over magnitude of v cross A. So let's find what dA dt is. So that's equal to, so that's sinh t I minus cosh t j plus 0k. We plug in for 0, that gives us 0, negative 1, 0. So let's put that in. So this is, so we have v cross A, that's 0, 1, 1, dot product with the value we just found, so that's 0, negative 1, 0, over our cross product magnitude, which is root 2. And then this becomes, so 0 times 0 is 0. That's negative 1 plus 0 over root 2. Sorry, and this is squared. So this is actually negative 1 over 2. May have failed to add that into this equation here. Let's make that fix. There we go. Okay, so those, that's how to solve every single one of those 6 components that were given to us. So when we do this, it's a good idea to have all of your calculations on the side when you need them. So rule of thumb to start things out, do velocity, do acceleration, do speed, do cross product of velocity and acceleration, then its magnitude, and everything else you can kind of work out as you go along. Okay. So example 16. So find the radius of curvature with center at HK and radians A. So we're not given our equation in this case, but from our previous chapter, we can find that this is so a circle. So when we parametrize a circle, so we're going to keep this in terms of h and k. So we have h plus cos, plus a squared cos t, and it's a squared because a is the square root of whatever lies under. Is that right? No, hold on. Nope, I lied. This is just a. Okay, and that's plus k plus a sine t. That's j. And what do we put for our k? We will just put 0. So we're going to have to solve for everything while keeping everything in terms of these variables h, k, and a here. If we were to take the derivative of this, we treat h and k as if they were constants. So those just turn to 0 when we derive them. So then we're only going to work with this part here. So then that turns to negative a sine t I plus a cos t, j direction, and we keep our 0 k hat. And this is negative a cos t plus negative a sine t j plus 0k. Okay, so we know for our radius of curvature, we are going to need speed over the magnitude of the cross product of velocity and acceleration. So we're going to need to find some of those values. So let's start off with speed, and that's equal to so that's negative a sine t squared plus a cos t squared plus 0 squared, and that's equal to a squared sine squared t plus a squared cos squared t. And we know that we have sine squared plus cos squared, that's equal to 1. So this is just going to be square root of a squared is equal to a. Okay, next up, let's do our v cross a. So we have our velocity, negative a sine, we have a cos, 0, 0 over here, and then we have negative a cos, negative a sine. So we're only going to have a k component, so we can say these are 0 because we have a row of zeros here. So then when we cover up these rows, we are going to have, so that's positive a squared sine squared t minus negative a squared cos squared t. So if we were to factor that out, so this becomes plus, and that's just like saying 0, 0, and this is like our previous one with speed. Sine squared plus cos squared equals 1, so that just leaves our coefficient a squared as our k component. So we take the magnitude, that's equal to, so that's 0 squared plus 0 squared plus a squared plus a squared squared. Those just cancel out, so that just gives a squared. So now we can solve for our radius of curvature. So we said we needed speed cubed over v cross a. So what's that equal to? That's a squared, and then our speed was just a, so it's a cubed. That cancels out, that reduces down to 1, so then that just gives us a. So radius of curvature is equal to a. And it's going to help us in some next questions. So that was just expressed as a plain old circle while keeping our terms in there as h, k, and a, and we found that a radius of curvature is just equal to saying the radius of the circle that we're given. And that makes sense because it follows the same path as that C. So now we want to find the radius of curvature given by the plane x squared plus y squared minus 4x plus 20y plus 23. So we're going to need to complete the square for this. So that means taking our x terms and grouping them together. So we're going to do x squared minus 4x. Going to keep those guys together. This is plus y squared plus 20y. And that's equal to, so let's kick that 23 to the other side, negative 23. So complete the square, we take our first term and our second term. We're going to take that second term divided by 2, which is negative 2. Add it to there. And then that's plus y squared plus 20y. Half of this term is 10. So then we add 10 to that side. Equals negative 23. And then we're going to take the new terms that we added. So we added negative 2. And we're going to add it to this side, squared. Then we're also going to take our 10 and square it. So then we can factor this part out. So this is x minus 2 squared plus y plus 10 squared equals, so we have negative 23 plus 4 plus 100, and this is 81. And we said from our previous question that our radius of curvature is just equal to our a. So this value over here right now is a squared. So once we break that down, it's equal to a, which is equal to 9. So that's our answer for this question here. And we were able to use this because we know that this was a circle, because once we had just one term on this side, there's no coefficients for either of our terms, for x and y. That means this is going to have the same radius for both of our x and y. So we know that this is a circle. That's why we could use this, which we got from our previous question above. Okay, so now we're going to talk about the banking of a road turn. So this is used to find the rate speed of our term. So I'm going to use this equation below. Our velocity is equal to the square root of our radius of curvature times our gravitational force times tan theta. And there's a better illustration for this. Let me just grab that. So tan theta is, so if we had a car here and it goes around a turn, theta basically just describes the angle that it makes with the horizontal in a circle. So we can use this value to find the safest maximum speed that we can travel within a turn without escaping our a certain curvature when we are executing a turn on a road. So if we were to apply this equation, so let's write it out. So in this equation, we want to find the banking angle. The units that we are going to use is meters per second for velocity. Yeah. So then it remains consistent with what we are working with. So we have our equation V equals rho g tan theta, and we want to find what our theta is. So let's isolate for that. So that's v squared equals, that's v squared over rho g equals tan theta. Now theta equals tan inverse v squared over rho g. First thing I am going to do is convert our velocity. So right now we are in 36 kilometers an hour. Let's convert our kilometers first. So we have 1,000 meters in a kilometer, and then in seconds we have, in 1 hour, we have 3,600 seconds. So then we take 36 times 1,000, divide by 3,600, and that's 10 meters per second. So then when we plug into our equation, theta is equal to tan inverse. That's 10 meters per second squared. Our rho is represented by this 50 meters here, and times gravitational force, 9.81 meters per second squared. And this gives us, so that's 100 divided by 50 times 9.81, and then tan inverse of that, which gives us 11.52 degrees for our angle of bank. So for our second part, relating to this kind of example, we want to find the velocity now, but we want it in miles per hour. So we are given 137 feet. So we're probably going to get feet per second as our velocity, right? So we end up for feet per second, but we want to convert to miles per hour. Feet per second to miles per hour is multiplied by 0.68. And that's what's going to convert it into miles per hour. There is a sheet on conversion rates included in the notes. If you need them, I can try and do a separate video or put them in the description. But I'm not sure how many people watch my videos, so we're just going to keep going. So that is V is equal to rho, gravitational force, tan theta. And so we're going to want to keep these units consistent. So if we're given 137 feet for our rho, for our gravitational force must also be in feet per second squared and not meters per second squared. So this is given by 32 feet per second squared. Then tan of our angle, 17. And this gives us, so that's 137 times 32 times tan 17. And this gives 36.61 feet per second. And to go to miles per hour, we know that we have to go 0.68 multiplied by our feet per second, which equals 24.89 miles per hour. So some of these questions can take a little longer to get through since there's a lot of components that are involved, especially with our systems seen above, right? There's a lot of work to be had with some of them. So you have to be really careful with your math and make sure it's consistent all the way through, and make sure you're plugging in your numbers as you go. It makes some things easier. Of course, when you are deriving equations, make sure you keep your variables in it. But if you're looking for things like cross product and magnitude, definitely you can use the plugged in values. All right, so that brings us to the end of this video. I hope you enjoyed. I hope you learned something, and I will see you in the next one. Thanks for watching.